Hello. I have a strong feeling I am live now, so just please say, Mr. Dharma, you're live when you hear me. That'd be wonderful. So today, wait, I'm just not sure yet. We'll find out. Hello. Hi, Rosemary, Zitong, Rohan, Nathan, Zach, Joshua, Lauren, John. Nice to see you guys. Just let me know you can hear my voice, and then I'll start. Yeah, perfect. Thanks, John. Functions. For us, functions are things that we write like this. Y equals something. So here I could write f of x equals something, or I could write y equals something, and that means the same thing. We write y equals if y equals x, or this notation here, it means function of x. It's kind of a really cool way of notating things. So it's a function of x as opposed to y being a different variable. So sometimes instead of saying y equals something, I might say f of x equals something. Right? The really cool thing about that is, let's have a look. If I said, here's an example. If I said f of x is equal to x squared plus 3. I don't have to do anything too weird to ask you, question 1, what is f of 2? What happens when x equals 2 in this function? Am I a little quiet? Okay, I can be a little louder. Sorry. How about now? Oh, oops. Yeah. I'm loud now. Tell me if I need to go quieter. Sorry, team. But I did this because Josh said I was a bit quiet. So I have f of 2. So instead of x, I'm going to replace it with 2. 2 squared plus 3. And so then 2 squared is 4. 4 plus 3 is 7. And so it's a bit of substitution, but it's a really nice way of notating stuff. So I don't have to go, what is y when x equals 2? I can just say, what is f of 2? Similarly, what is f of 4? Thank you, Rosemary. Yeah. F of 4, I just substitute 4 squared plus 3. So that's 16 plus 3. That is 19. But I want you to be very careful. Let's do f of negative 3. Okay. Brackets are really important. Okay. It's negative 3 squared plus 3. Negative 3 squared is positive 9. And then I've got another 3, so it's 12. And so what I typically and a negative number squared. So this is a function. This is a function notation. Right? But then when we graph this, draw a little axis for you. Alright, and I'll get rid of the ruler. I can graph some cool looking things. Carefully, right, if I pick a point, the y value is a function of x. And the word function's key here. It's not any graph is a function. Only certain graphs. If you can draw a vertical line through a graph and it only hits it once, So look, this ruler only goes through this graph only once ever, vertically, and then it's called a function. So let me draw you an example of something that's not a function. So if I had this circle, or attempted circle, that is not a function. That's an n, thank you, Nathan. But no, this is not a function, right? Because if I took a vertical line, I'm going through once and twice in some cases. And in some cases, I'm not going through at all. And so because of that, in some cases, I'm going through it one time. Because of that, this here is a function, whereas this here is not. A circle is not a function. All right? And so a function is this called the vertical line test. You can only have a function if it goes through once, not more than once. Okay, let's get rid of that. Okay? What's interesting? Well, after I get functions, I get graphs. A graph of a function, each x value gives only one y value. Right, and that's how you can tell it's a function. So if I pick x equals 4, if that's 4, the y value is 0 here. Okay? If I picked x equals, I don't know, 6, that's not 6, we'll call that, I don't know, 16, no, we'll call that 12. Then the y value is also 0 there. Right? Each x value only gives you one y value. Okay, and that's how functions roll. Okay? And functions have some interesting features. Right? If you draw them, each x value only gives you one y value, that's cool, but they have properties. Okay. Okay. And these properties that I want to talk about, I'm going to list them out for you first, and then we're going to talk about what they are. There are some physical properties. Symmetry. So, this is like whether there's mirror lines. Can you find any mirror lines? Symmetry is a fundamental property of graphs. What other things? And I'm going to go back to algebra. I'm going to call them x-intercepts. But they're kind of like roots of equations, right? So symmetry, x-intercepts. So like, do we have parts that cross? How many times does this cross? Once, twice, 3, 4, 5 times, right? It's really important to know whether it crosses. Okay, for this one here, let's draw a function. Okay, I'm going to draw a function. Yeah, can you sort of see that there's a mirror line there? Okay, that tells you symmetry. This tells you x-intercepts. Another really interesting thing is turning points. turning points, or maxima and minima, right? This is a plural form of maximums and minimums. They kind of give you an indication as to the top point or the bottom point of each little part. Do they have maximums and minimums, or where the graph changes which way it's going? Okay, kind of a crucial part of graphs. So these are the three visual elements of a graph we call properties, and then there's two algebraic elements. Not algebraic, but like more equation based, and it is the domain, which is set of x values in the function or graph, and then we have the range, which is the set of y values in the function or graph. You're like, Mr. Dama, why is that really important? Well, if you can define all of these, then you can sort of see what your function's going to look like. Okay, what x values will your functions be defined for? What y values will your function be defined for? It's kind of important. Okay, let's have a look at an example. Let me draw a function. Okay, a real simple function, a basic function that you guys should be familiar with. Tell me if you know the equation of this function. Right, that's my best drawing. Making sure I draw arrows. This is x, this is y. Tell me if you know that equation. And then what we're going to do is we're going to list off these key things. Do we have symmetry? Do we have any x-intercepts? Sound off in the comments if you know what the answers to this are. Do we have any turning points? And I'm going to just quickly outline. I'm not going to give you any more than that. Yep, Rosemary, well done. This function is y equals x squared. Yep. Yeah, well done, guys. Yeah, Josh, yeah, you're a bit more, yeah. But I'm just looking at y equals x squared. And y equals x squared, do we have symmetry? And the answer is, I'm going to write it as a sentence. There is a line of symmetry at x equals 0. Meaning that when x equals 0, so this line right here, sorry, I'm trying to draw it next to it so you can see. When x equals 0, you get this line here. You have the whole graph is symmetrical. Does it have x-intercepts? Yeah. There is one x-intercept at 0, 0, or x equals 0 and y equals 0. Right? That's an x-intercept. I don't need to write the y equals 0. X-intercept is when y is 0, so I don't need to write anything more. Okay? And then, is there a turning point? Is there a point where this graph flips around? Well, you start coming up from here, and then you go up. And so I would argue that there's a turning point at this point here, and I would say there is a turning point at 0, 0. And the other thing about it is a minimum. Okay, why is it a minimum? Because it's the lowest point. Okay. Now, for this function, let's write what our domain and our range are. What x values can I possibly plug in that will give me an answer? Is there any x values I can't plug in? No. Any x value I plug in will be fine. So, the domain is all real numbers. And if you realize that that word real comes back in, just use it for now. We'll talk about it a little bit later. What about the range? What kind of y values will I get? I've got y is positive numbers here, and the smallest y value is a 0. So I can't get y that are negative numbers. The range is y is greater than 0. And we draw squiggly brackets around that. If you're not sure how to draw squiggly brackets, let me draw a nicer one for you before I draw a mathematician squiggly bracket. It starts like an... Oh, I've got to draw it fast because my laptop doesn't like it. That shape. But as you sort of speed up, you end up getting slightly mangled of this. Alright? So that is called the range. The range is y is always positive or 0. So y is greater or equal to 0. That's the range. And the domain, x can be anything. And those are the 5 key ideas that we need to be able to define for any function. Is there symmetry? Are there x-intercepts? Is there turning point? What's the domain? What's the range? And we can do that. John, you're right. Is the domain real for every graph? No. And you're like, but sir, where could you have a graph that well, let me draw a function for you. Okay, we will look at this function later on in the week, but okay, here is my function. It goes. Ooh, hello. Let me try and draw this a little more carefully. Okay, it goes like this. Okay. Right? And so this function here, this is called a logarithm. So we've looked at logs. Well, actually, you've looked at logs, haven't you? F of x equals, I don't know, I'm going to call it log of x. We've looked at logs, right? Remember, you couldn't take logs of a negative number, right? So the domain for this, oh, so the domain for this just write in orange. The domain is x greater or equal to 0. And as you can sort of tell, my squiggly squiggle thing goes from being really, really good to really bad. And so, yeah, those guys. These brackets are possibly like the most mathematician things you can ever do. So get used to drawing brackets, because the better you are at drawing them, the better mathematician you will be. Facts is facts. So that's enough of that. But the domain here is x is greater than 0, but the range here is all real numbers. But I'll come back to this graph later on, okay? I'll come back to this later on, but the fact is, sometimes the domain is not just that, okay? You're like, okay, Mr. Dharma, give me another example. Well, the diagram. I'm going to draw this graph here. I'm going to say this is 2 to 5. I'm going to say that this is 3 to 8. Okay? Scales don't matter. I don't care. Okay? What is the domain? Once again, the domain in this situation what is the domain and what is the range? What are the possible x values for this function? Well, the domain here is from 2 to 5. I'm going to write that again, guys. Sorry, I focused too much on my brackets. My computer's lagging real hard. Here we go. There we go. X goes from 2 to 5, and the range goes from 3y to 8. Okay? And so now the domain is all the x values that we could have. See, the function is not defined anywhere else. It's just that small section of that graph. And the domain is all the y values, and it's just that small section of the graph. And that's why domains and ranges are really important. Anything except -2 or -5? No. It's in that range, only in that range between these numbers. And this is why when we're doing when we're doing quadratic equations, I was getting you to be very, very particular about using these between situation. And Monique, the reason we need these brackets is because they are how we define a domain. Just like these brackets are how we define coordinates, these brackets are how we define domain. And it's really important that we get notation down, really important. Okay? So the domain is all of the x values that we can have, and the range is all of the y values we can have. Sometimes they might be infinitely wide, sometimes they might be very, very specific, right? Sometimes, depending on how much of a graph you've got. Sometimes when we learn these graphs, it's really important to restrict your domain or restrict your range. And so later on this topic, we're going to be looking at, so we're going to be modeling, right? And when we model, so if this is X and this is Y, and suppose, like, I don't know, I have a graph that's like that. I might just model this part here, and I might model this with a straight line. I'm going to use a different color. Let's go. Suppose I had that picture there. Oh, yeah. Suppose I had that picture there. I could model this with a interesting curve. I could just model this part here. And I could say that that is my domain and this is my range. So my range is between those two and my domain is between those two. And that's only the part I'm modeling. And you're like, why would you do that? Well, you know, I don't know. If I gave you the McDonald's arches and I asked you to come up with an equation for them, you might want to just model some part of it. Or, you know, I don't know. We're looking at exponential growth. I know we've had coronavirus, and coronavirus has been really interesting to model. And people are like, you see these models that are coming up like this, but they're like, this part is really important. So they might want to just model one part of the equation. And so what I'm saying is, knowing what part you're modeling can be restricted by your domain, and your range will reflect that. So if you're only modeling, you know, or sometimes you might model something, but it doesn't happen forever. Or you might have a model that goes into negative but doesn't make sense. So let me draw another model. Let's go back to our parabola looking thing. Right? Suppose I had along here, this was time in minutes, or in days maybe. And this is the number of cases of coronavirus, right? I'm very impressed with that curve. Can I get like some applause for that, guys? I think I deserve it. Okay. You know, and it might be the case that the number of cases for corona started like, well, and then on the first day you might have had this many cases, and then this many cases, then this many cases, and then this many. Right? My model doesn't fit here. And surely, like before I started measuring, it's always 0, isn't it? And so I wouldn't say that my model is perfect, but I would definitely say that I would like to restrict my domain of my model from here to here and say that this part of my model is really good, and before 0, the model is terrible. Thanks, guys. Yeah. That's what I'm wanting. Yeah, like, how terrible is the model before it? Well, it's pretty bad. And so I might look from 1 day to 36 days, and I'll say my exponential model is really nice, right? But then it might be the case that my model continues up like this, but the cases might level out, and we might not get any more new cases. And if that happens, my model, I wouldn't look at this part of the model. I'd go, that's pretty bad. And I'd also say that this is pretty bad. Right? Only this middle part is really useful for me. And so this is why my domain won't always be infinite. So depending on what I'm modeling, what I'm looking for, I'm going to be very selective as to how I'm going to build my model. So domains are all the x values that you're looking at. So I'm going to look at x from 1 day to 36 days, and that's going to be really interesting to me. And we're going to look at from like 500 cases to 50,000 cases. I don't know. I'm not sure. Right? Those are the cases we're going to look at. But then after that, this red line is a terrible model. I wouldn't use this red line to predict what's happening on day 40, because day 40, we've eliminated coronavirus in New Zealand. Or I'm not going to look at it, what happened 5 days before today, because this is when I started getting coronavirus in New Zealand. And so it doesn't make sense that we've got this number of positive things when it doesn't really happen. And so this is what modeling is. This is why domains and ranges are kind of important, and why it's really important to come back to these 5 really key ideas. Do we have any symmetry? Do we have x-intercepts? Do we have turning points? Remember, turning points might indicate maximums or minimums or reasons for things to change. And x-intercepts. X-intercepts typically indicate when something stops. So we were looking in the coronavirus, we're looking for when the number of cases hit 0 again, or number of daily cases hit 0, meaning there's no change. That's really interesting to us. Or, if you're modeling the speed of a car, when it hits 0, it's when the car stops. Yes. Right? Now, coming back to this, symmetry. Symmetry is kind of important as well, because if you have symmetry, you can say, I don't know, if you're going around an athletics track and your speed, you speed up the same as you slow down or something, that might be really useful. Or, I don't know, if you're measuring the spinning of your wheel and it's not symmetric in how it accelerates, then you've got issues. And so these 5 things are things that we will start talking about. Okay. Also, Josh, those square brackets can be useful. Okay, but guys, let's have on-topic conversation, eh? So what I thought we'd really just touch on is today. That's it, right? Know what a function is. So using function notation is really, really important. So there's plenty of stuff in our book. I will be uploading a document that your teachers will share with you soon, which will give you an indication of exactly which pages I want you to watch after each video. But please come to every live stream. This week we've only got today and Thursday, and today and Thursday, and next week we've got Monday and Wednesday. And we will try to figure out the rest of everything soon, but try to indicate what domains, what ranges are, and try to have a play around. And then on Thursday, we're going to be talking about parabolas and cubics and how we model them and how we can plot them on Desmos as well. Okay? Does anyone have any questions before I sign out for the day? Cool. So thank you for coming to this live stream. Please try to talk to your teachers, ask if you have any questions. But this is what functions are. Functions are defined as functions of f of x, and it's just an easy way for us to write notation, for us to do some substitution. And remember the vertical line test. A function is only defined if you can draw a single straight line through. Are you going to talk about input and output? No, input and output are, so input is x values, output is y values, right? So input is domain, output is range. Cool, thank you Ava, thank you Monique, thank you Ty, thanks Najaya. Yeah, so domain is only the x values and range is only the y values. All right team, I'll call it a day. Yeah. Matt T. Function of x. It's just notation, Matt. Um, it's an easier notation because if I wanted, if I had f of x equals x squared plus 5x, and I had y equals x squared plus 5x, if I wanted to know for this one here, find, that's not meant to happen. Find y when x equals 1. So versus, for this one, just asking what f of 1 is. Which one's easier? Okay, so Matt T, that's why I would do that. Alright, so f of 1, easy, 1 squared plus 5 times 1, 6. Whereas here, I have to go y equals also 1 squared plus 5 times 1. That's cool, but the thing is, the way I've written the question is I've had to use more words, and that's not how you do things. Can I put this on your classroom? Maybe. We'll see. Maybe. I'll send it out to your teachers. Does that make sense, Matt? Okay, it seems to be a lot of people that want a screenshot of all of this, even though you can watch the video again, but I will make it available. Okay? Okay. All right. Well, I'll talk to you guys later. Thank you. Bye for now.